that we love our customers and we love meeting our customers. So it's wonderful to see you. Thank you very much for being here. And in today's session, I will not be talking very much about the user interface, the input, and so on, because PIPENET is very, very simple to use and it's very intuitive. And for that reason, it is really not necessary to demonstrate the input. And in fact, as I demonstrate the program, you will almost certainly learn everything that you need to know about the interface and input as we go along. I may make a few comments here and there. The main example I would like to use is a very, very simple one, and it is specifically for the purpose of demonstration and training. It is not a real system. It is here simply because there are certain features of PIPENET that I want to show you. And that is why this example is here. And I hope you can see my screen, in which case you will see the example. It is actually a closed loop system with 3 heat exchangers in parallel and with control valves, flow control valves. And we'll see later on that this technique can actually be used even if you did not have control valves. For example, if you had orifice plates or manually adjusted throttle valves, you can use PIPENET to size the orifice plates or to estimate the position of the throttle valves. So simply because I've used a control valve here, it does not mean your system physically has control valves. It is a design methodology. That's the first thing. And the second thing is that I will assume that this is a brand new system. So you do not know the pump size, you do not know the pipe sizes, and so on. And you do not know at this point how to model the closed loop. And I will go through that step by step. It doesn't mean that you must always start with the system with the diameters unspecified. It is just that I want to go through from a clean sheet of paper where you have very little information and you have to design the system. And you can start at any point in the methodology that I will describe. So let's go into PIPENET now. This is a system that I was using earlier. So that is the system that I showed you just now. Where do we start? See, I will start with the system defined in this way. You can see that I'm showing the pipe bore or the nominal size, and that is unset. So if I click on a pipe, you will see the diameter is unset, but the length and the elevation change are given. That's because the starting point has got to be something like the plot plan, because if you don't have any information about the layout of the system, then of course you cannot design the system. So we have to start somewhere, and we assume that we have some information about the rough layout of your system. So you will know the length and the elevation change. There are actually 4 windows in the system. I will describe them very quickly. This is called the drawing area, which is where the schematic drawing is shown. And this is called the properties window. And if I click on a blank space on the schematic window, it'll show you the number of items used and the maximum allowed. So you can see that the maximum allowed for pipes is 10,000. That may seem a big number to you, but in fact, there are systems with 9,300 pipes that people have modeled. And so, we're getting fairly close to that limit. So people are solving very, very large systems indeed, especially when it comes to firewater systems. The standard module systems tend to be smaller than that, but nevertheless, you can go up to that many pipes. But if I click on an item, it shows the attributes of that item. Now that became black because I've already chosen this. If I have none, then the item that I select becomes red. And that indicates what the properties window refers to. And after a calculation, you will see the results here. This window here is called the schematic overview. It is also called the bird's eye view. The reason is that it's got the complete network. Within that, there is a red rectangle which shows the zoomed area. Because if you have a very complex network and, with, let's say, 100 heat exchangers, and if you see something like that, it's quite difficult. It'll take you time to work out where you are. And this is very useful to tell you in an instant where you are. The second purpose of this, you can actually click on that rectangle and move it about. See, for example, if I show the nominal size, which is of course unset at the moment, and if I want to see what they are, we'll have a look at it when I do a calculation. You'll find the use of that. Now this is called the data window, and in this case, because I've shown pipe here, it is displaying all the pipes in the system. I could, for example, show the heat exchangers, and it'll show the data for the heat exchangers. And don't forget, there is a tab here, results, and that will show you the results after the calculation. Okay, you can maximize this, then right-click, scale to fit. I'm going to do the first step, which is to size the pipes. What do we need to do to determine the pipe sizes? First thing is we need to select a pipe schedule, because it's no use coming up with theoretical pipe diameters, because you're going to work with a pipe schedule and you want PIPENET to show you the nominal sizes in the pipe schedule rather than the pipe IDs. So first you have to select the pipe schedule, and then you have to give the maximum velocity, because typically the pipe sizing is based on the maximum velocity. How do we do that? options. This is pipe type. That has the dual purpose. See, the pipe schedule I've selected there. If I want to add another pipe schedule, I just click on that and select another pipe schedule. You can have up to 10 pipe schedules in one system. If I click on that, then you can see the maximum velocity that I've used for pipe sizing. And that is what pipe type means. It's got two purposes: the pipe schedule I'm choosing and the maximum velocity. Even if I already specify the pipe nominal sizes, the maximum velocity will be used for diagnostic purposes. So if a pipe exceeds the maximum velocity, then PIPENET will give you a warning. So it has many purposes. So based on that, let's do a calculation. By the way, because without the pipe diameters, you cannot size the pump. So the first step is to size the pipes, and that is what I'm doing. These three buttons, B, D, and A, are important, and I will describe them later on. Click on that. You've got the pipe diameters. If I go to the data window, you can see the diameters there, and you can also see the diameters have a yellow background. The cells have a yellow background, and that is because it's to indicate that PIPENET can change these diameters, and that's the reason for the yellow background. Now let's go back. I must activate that window, so I click on that. Let's talk a little bit about what these three buttons mean. In this case, we've got one input and one output. If I click on that, you can see that there is something called design specification and analysis specification. It's because B stands for both. It means size the pipes as first step, and as a second step, do the final analysis calculations using the pipe sizes that PIPENET has selected. So that is why there are two sets of specifications. Why are they not the same? And there are two reasons for that. The first reason is you may size the pipes under one set of conditions, but you may wish to do the analysis calculations as to how the system will perform under another set of conditions. That's why there are two sets of specifications. Second reason is that if you think about it, the pipe size is a function of the flow rate. So if you have many inputs and many outputs, the design specification will have one pressure and all the others will be flows, because you want PIPENET to size the pipes in order to accommodate the flow rates which you require. So that's the reason why there are two different specifications. When it comes to analysis, the specifications can be in any combination of pressures and flow rates as long as there is one pressure and the number of specifications is equal to the number of inputs and outputs. We call them I/O nodes. So the number of inputs and outputs will be the total number of specifications, and you must have at least one pressure. Okay, so PIPENET is an ideal tool for optimization because you can save a lot of money by optimally designing the system. So we've got this here. So what do I need to look at now? The first thing, let's go to the output and have a look. Let's go straight to the end. See, I've chosen materials takeoff. If I choose materials takeoff as an option in PIPENET, you will see that this table appears. So it shows you first the nominal size, and as I said, you can have up to 10 nominal sizes, and it will show you for each size what length is the total length. And from this, you can actually work out the piping costs. You won't simply, of course, estimate the cost of these pipes because you'll have to apply some factors in order to estimate the total installed costs of pipes. You can also see later on here, it's showing the number of valves, the number of heat exchangers, and things like that. So that materials takeoff will help you to estimate the piping cost. Now we've got the delta P, the pump must generate. I can display that to a greater accuracy. See, I'm doing all this deliberately to show you the important features of PIPENET. So if I change the number of decimal places under display, say it'll show it to a greater accuracy. And so with these pipe sizes that I've selected, the pump must have a capacity of 900. See, this is another useful feature because there is color coding. And using the color coding, you can actually very quickly see where the bigger pipe sizes are. Anyway, we know that the pump must generate 8.823 psi at 900 US GPM, gallons per minute. By the way, it's US GPM. Keep this in mind because that's different from the gallons which are used in many other parts of the world. And so do make sure that you use the right choice for the gallons per minute. Now you're looking at this and saying, hey, I don't know what is meant by gallons per minute. I don't use gallons. So it's no problem. So you click on units, flow rate, talking about flow rate. See, it's US GPM and there's also UK GPM. If you prefer to work with cubic meters per hour, you choose that. And with pressure, if you want to work with bar gauge, you choose that. And you click, and you have the results in cubic meters per hour and bar gauge. So you see, you can see how easy it is. And the report will also, because the report is produced during the calculation, you'll have to do the calculation again, and the report will show the results in the new units you've chosen. The reason why I'm talking about this is because if your client, if you're an engineering company, your client may have their own preferred units, which are not the same as the units in which you would like to work, because it's always a great idea to work in the units you're familiar with, because you have a feel for the numbers, and if there is a mistake, you will know immediately that something is wrong. But at the end of the day, your client would prefer to work in their own units, and you can change the units after you've done the fine-tuning and you've completed the design, and in your reports you can submit the results in the set units preferred by your clients. And if you're a client, if you're an operating company, of course it's the opposite. You have the freedom to specify the units that you want, and the engineering company or the consultant who is doing the work for you, they can work in their preferred units but submit the results in your preferred units at the touch of a button. You don't have to do anything. Let's go to this. You see here, you've got all the diameters. Now that's with the B option. What does the D option mean? I'd prefer to start again because in order to get rid of all these numbers, let me start the file again. See, this is what we started with. We go to the D option. It's not very often used, but you should know what it is. I choose the D option. I still have the design specification, but the analysis specification is not here. Why? Because D means design, which tells PIPENET, do the pipe sizing, but do not do the analysis calculation. You do that simply because there is less input. If you're only interested in optimizing the system in terms of the piping cost, then this is a good way to proceed. So I do the calculation now. See, it's showing the diameters, the files for the flow rate. It will not display it because it has not done the analysis calculation. That's what the D button means. I will explain the A button in a moment. That because that's another option. In fact, A is the most commonly used option, and we'll look at that in a minute. So let me go back to the original file. Right-click, scale to fit. Do the calculation again. You can see that it's populated the diameters. My purpose is optimization, ensure the pressure. I can change. I'm repeating these so that you can remember what I'm doing. So it's showing all the results through 3 decimal places. I mean, normally, of course, with pipe diameters, it will not work to 3 decimal places. You can also change the number of decimal places individually under units, but I will not go into that. It's just a waste of time. So I've got this. Now, as optimization, what am I going to do? I'm going to change the velocity I'm going to use, and I will do the recalculation. You can see that the pipe sizes have decreased. And I've got the delta P of the pump at 21.1 psi. The flow rate, of course, is the same as before. By the way, you may see that the flow rate here is slightly different from the flow rate there. That's because there are heat exchangers and the temperature changes. That's why the flow rate before the heat exchanger is less than the flow rate afterwards, because the temperature increases. You can actually show the temperatures. You can see that the inlet temperature of the heat exchanger is 30 and the outlet is 51.8. And because of that, the volumetric flow rate changes very slightly. So we look at this, and and let's go back and have a look at this as well. And as you know, you can show these legends, which are quite useful. And you think, I'm a good boy. I've done the basic design. And then you suddenly see, oh, there's a diameter of 125 millimeters. And I think to myself, that's a non-preferred size. I should not have it in the design. So how do I stop PIPENET selecting these sizes during the design process? Let me put that back to the pressure. Go to options, the pipe type. See, PIPENET is very much an engineer's tool, and these are all things that you would want to do. That's 125. I click on that. See, there is this button here, avoid in design. I click on that. Click on OK. Because these diameters are not permitted anymore, so they've disappeared. I do the calculation again. They've been increased to 150. You can also see the delta P that the pump needs to generate is less. So you see, this is the step. These are steps in the optimization, because depending, PIPENET runs very, very quickly. So you can change the maximum velocity you're going to permit very quickly and do the calculation. So, and then you can estimate the operating cost from the hydraulic power of the pump. We'll come to that in a minute. PIPENET can calculate the hydraulic power. But here, knowing the delta P and the flow rate, you can estimate the hydraulic power yourself. So that is a measure of the operating cost. And you also have the capital cost, because you can size the pump and you have an estimate of the piping cost. So that is the way you do the optimization. So we've got all the diameters, and I'm happy with the design now. What do I want to do the next? Now, before that, I'll show you some interesting features in PIPENET that you may find useful. See, there is this thing called the area tool. Let me switch on the grid. See, you can see that it's got orthogonal grids. You can also have isometric grids. Let's stay with orthogonal grids. Using the area tool, see, I can select. Let me just unselect them. So the area that I've selected is in red. So it selects the items which are completely within the area tool. Then I can right click, copy, right click, and paste. So it's produced another copy of that. It's convenient to pick a node so that you can more easily position. I can move it. Then I can pick up the pipe tool. I want to create a waypoint. Press and hold the shift button. Click on the left button of the mouse. Do the same again. I'm holding on to the shift button. I want to create a node here. So I release the shift button and click. I do the same on that side. See, in creating this network, I copied and pasted a complete network, but you can also copy and paste attributes. So I can, for example, copy, right click, paste, right click, and paste. So in this way, you can actually, if you have a repetitive pattern in your system, you can actually copy and paste subnetworks to build a big network. You can also do this, that if several of you are working on a very large network, each one of you may analyze a subnetwork, and you may have data files with subnetworks. You can actually also open, copy and paste subnetworks to create a big network. I mean, the 9,300 pipe system I was talking about, that's the way it was built. I mean, one engineer didn't sit down and input 9,300 pipes. You know, that is not a nice thing to do. But they observed the repetitive pattern and copied and pasted the subnetworks to build the big network. Having done this, I can actually do the calculation. See, with these three heat exchangers, we had 350, 300, and 250. But it's in addition to that, I have 350 and 300. So it's 550. So originally I had 900. So I should actually have 1450 here. It's pretty some warnings because the velocities are probably high in some pipes or something. Anyway, let's have a look. So it's calculated the pipe sizes for the additional part of the system. Okay, so let's copy and paste. We can also do this. See this, undo. Okay, so I'm back to what I had before. Of course, I should put it back to 900, which, because I did the undo, it's gone back to 900. Be sure to do that. Okay, now, one thing I should explain here See, these two heat exchangers have got the flow rate. They've also got the flow control valve. The flow control valve, I could have had any of these options. Because as a flow control valve, I chose the flow rate option and specified the flow rate. I've used the model elastomeric valve. It's a very versatile model, and use that wherever you have a situation like this. Don't use the control valve, because for the control valve, you must specify the CV. And this, if the CV is wrong, in other words, the CV could be easily wrong if you start with a system that you've not designed properly, in which case you may find that the system cannot work. And so you may find that the simulation fails because the system is infeasible. So always use the elastomeric valve in the starting case. The reason why I've not got a flow control valve here is because I've defined the flow rate here. Why did I define the flow rate there? It's because with the system, I explained to you earlier that with a system with one input and one output, in other words, two input-output nodes, you must have two specifications, at least one of which must be a pressure. So I could have given two specifications here and left that unset, but nevertheless, I must have at least one pressure. And in the design specification, I must have one pressure and one flow rate. And that's what I've, and if I specify the flow rate here, I cannot also specify the flow rate in each of these legs, because there could be a contradiction. Mathematically, it's called linear dependence. You may find that the sum of these three flow rates that I've given, they do not add up to the flow rate I've given here. So there could be a contradiction. And so you will find that mathematically the system becomes linearly dependent and you cannot solve it. That's why I've given the flow rate here, and the flow rate through the two flow control valves, that will in fact automatically fix the flow rate through this leg, because this 900 minus the 350 minus 300 is 250, which is what that heat exchanger requires. So, you know, that's the reason why I've not defined a flow control valve here. Okay, so do the calculation. The pipe diameters are here. Now let's go to what is meant by the A button, because here you see I've optimized the system. I'm happy with the design. What I want to do is fix the diameters to these values, because if I do not fix the diameters to those values, and if I change the flow rate somewhere, then the diameters will change again. I want to avoid that. I want to fix them. I'll click on A. See, proceeding will fix all calculated pipe diameters. We click on that. Now the diameters are fixed. You might wonder, why is this yellow background there because I need to refresh. See, this is another thing see, this is how you open these windows. You can close them and you go to view and open the window. So now the background has become white. What does that mean? It means PIPENET will not change the diameters by itself, but you can manually, of course, change it. Okay, it just means PIPENET does not change the diameter by itself. So it's now fixed. Do the calculation just to make sure that the results are the same. Now I said that the data window has one feature that's very, very important. Suppose, what is the first thing you'll do when you design the system like this? You will want to look at the results. Click on that. It shows the results. I may wish to see where is the pipe with the maximum friction loss per unit length, because by way of optimization, that may be what I want to do. Or I might want to see where is the pipe with the maximum velocity. I've chosen the velocity of design at 6, so all the pipes will be less than 6 meters per second. But I may want to see where is the pipe with the maximum velocity, or where is the pipe with the maximum friction loss per unit length. See, PIPENET, we pay a lot of attention to small details. See, it shows the pipe friction per unit length and static head loss separately. Why does it do that? Because you have no control over the static head loss, because the elevation change is fixed. You cannot change this, whereas you can adjust the pipe diameter in order to reduce the pipe friction per unit length. So you want to separate this from the total pressure loss per unit length. That's why it's got 2 columns. See how much attention we pay to detail, because this is what you want to look at when you're actually designing the system, because generally you cannot change that. Okay, so let's see if now you can see that there are different values, and if I want to determine the pipe with the maximum friction loss per unit length, one way is to go through this column. You can see that there is pipe, but supposing you have a system with 2,000 pipes, it will take you time to find out which is the pipe with the maximum velocity. And then you look at the label, which is 4, and then you have a look at this here. PIPENET can display the labels, but even so, if you have a system with 2,000 pipes, it's going to take you time, and this one feature in PIPENET will save you hours of time. I click on that. See, it's reorder the pipes in increasing order of pipe friction per length. I click again, it reorders the pipes in decreasing order of friction loss per unit length. So if I want to see where is the pipe with the maximum friction loss per unit length, just click on that, and that will take you straight to that pipe. So you don't have to go around looking for the maximum value and then see where the pipe is, which pipe. And then you can focus your attention on that pipe and try and reduce the friction loss. See how easy it is to optimize the system. It's a very much an engineer's tool. It is very much in tune with what the engineer wants to do. So that is the sorting facility. Another feature is that you may find that you need to look at some pipe. Let's say you manually scan this and look to see the maximum friction loss per unit length is on pipe 4. There's another way, and look for pipe 4. There is a search facility. It's already there, so see, it will go straight to that pipe. So you have the search facility as well. These are all features that you'll find very useful and will save you a great deal of time. We've got that now. Now, see, there's this black arrow and also the red arrow. What's the difference? Until you get quite experienced, don't use the red arrow, only use the black arrow, because this shows you the direction of flow, whereas that shows you the direction in which you input the pipes. That's the difference. Okay, that's actually not that useful, and you may find it quite confusing. So do not use the red arrow until you become an experienced user. So I've got this now. What's the next step? I want to select the pump because I've determined the pipe sizes. I know what they are. I've got is 16.696. So I want to select a pump that is going to deliver a minimum of 900 at 16.696 psi. So, of course, I'll choose a pump that's slightly bigger than that, and that's what I'm going to do. How do I input that? I go to the library, coefficients unknown. I'll explain some of the other things here. You can have fittings. See, you can have a user-defined fitting. If I click on that, then this becomes active. So if you have a rate bend, a 90-degree bend with an R/D ratio other than 1.5, you see the 90-degree bend. The built-in value has an R/D ratio 1.5, which is the standard configuration. But you may have a long radius bend, in which case you can specify the R/D ratio here. You can have multiple bends and so on. So you can define your own fittings there, and you can define control valves and things like that. Anyway, I'm going to input a pump curve. I click on new. This new pump. I put the values. What I had was at 900. I needed 16.696. I'm going to input the actual point from the pump performance curve, because the pump performance curve will be slightly bigger because I will choose a pump that's slightly bigger than the smallest pump that I can get away with. So I've taken some points from a pump performance curve. This, by the way, of course, is a hypothetical curve. (16.1), and they don't have to be in the increasing order. I would normally input that first because that is usually the best efficiency point of your pump, and that's one of the criteria you would use to select the pump. And the maximum and the minimum here represent the ideal range of operation, because there are rules regarding the ideal range of operation of a pump, because it depends on the efficiency, and also something called the run out point, because every pump has something called the run out point, and if you try and operate the pump with a higher flow rate than the run out point, then the performance of the pump will deteriorate very quickly. You can vibrate and so on. So it is ideal to operate within the preferred range for the pump, and that's what I'm specifying here. And this minimum maximum do not have to be the same as the minimum maximum here. So I'll click on that. Here, a couple of points. It's a smooth function I've chosen. I'll come back to that in 1 second. What I will also show is that how much attention we pay to detail. Because if you go to a pump manufacturer and say to him, Mr. Pump Manufacturer, give me your performance curve, he's going to give you a graph usually. The graph, unfortunately, has the head in meters, not in PSI. See, I've given the values in PSI here because that's what I calculated. See, you can have the pump head in meters because pump vendors normally publish the performance curve in meters head rather than in bar. That's a good reason for that because, as you know, the centrifugal pump, the pump curve in meters or the head will be the same for all fluids. So that's the reason why they do that. Anyway, here, because this is a demonstration, I'm working with PSI because I wouldn't want to use the same points here. This is, see, I've given 4 points. And the smooth function or the spline function makes the performance curve pass through all the points. That's why it's got a slightly funny shape. If I choose quadratic, then it looks more like the pump curve I want to perform. Now, one point here is that, misconception here, not so much now, but in the early days of PIPENET, people sometimes used to ask, well, I've defined the minimum and maximum flow rates for the pump, and the pump run out point is this. Yeah, but how is it that your PIPENET gives an operating point which has a flow rate higher than that? Now that's a good explanation for that, easy explanation, obvious explanation, and that is if you give the minimum maximum, it actually represents the preferred range of operating the pump. The pump can freewheel. For example, if you have a pump which is connected to a holding tank, and on the outlet side, the discharge flange is not connected to anything, what do you think that pump will do? It'll work above this flow rate. It will not suddenly stop saying, hey, that's a working range. I cannot work outside. It can work outside this range, except that the pump could vibrate, which could lead to damaging the bearings, and it could have cavitation and all that sort of problems. That's why we have this preferred range. But you may want to know, how will the pump perform outside that max preferred range? You see, that's why this degeneration factor is here. 5 is a good value. If I choose that, click on that. See, it provides a dotted line, because essentially this is an unstable part of it, but your pump manufacturer should be able to give you a rough curve for how the pump may operate above the maximum recommended flow rate. And you can change that. If I make that 7, click on that. So you can adjust this value to match what the the pump vendor gives you. So I'm going to select that pump, and that's it. Now I'm going to complete the network. One of the things I have to do is to select the pump, because your library can have a number of pumps. And so I have to click that. Select the pump. There's no longer an output. See, I'm teaching all little new features. See, I can right click and explode. So I don't have to input the pipes again and so on. I can simply explode the node. And as I said, use the elastomeric valve. Even if you're going to have an orifice plate later on. This is the closed loop system, but you cannot calculate a closed loop system completely. Why? Because you must have something to fix the pressure in the system. And here, see that we had a makeup tank. That see how these are the cases I'm going through. I'm going through all of them one by one. So that's where the makeup tank is, and it's convenient to break the network there. In reality, these two are the same point. So it's, for modeling purposes, what I'm going to do is call that an input. By the way, because I switched to A, you only have analysis specification here. Yes. I'm going to specify the pressure at 60 psi. That's about 4 bar. I also need to fix the flow rate there. Let's say that's 250 because that's what the heat exchanger needs. Having done given the pressure there, I can copy. And paste. See how much time you can save, and then change that to output. Okay, with any luck, the system should run. Click on the pump. See, it shows where the pump is operating on the pump curve. It is not, it's within the preferred range, so I'm quite happy. It should do because, you know, if you remember the operating point that that I determined was actually the pump curve was covering the preferred range, so it should operate in the right range. One important thing here, it shows the hydraulic power of the pump, which is very useful for optimization. We'll see an example later on where this actually shows you how important it is. You also have NPSH, that's to assess if there is the possibility of cavitation. Okay, and the volumetric flow rate and so on. So I've now solved the problem. And this is a complete system. That's a couple of things I would like to show, and I mentioned them earlier on. By the way, there's something I'd like to show you, which I didn't earlier. And that is this polygon tool. So I showed you the area tool, polygon tool. In order to use the polygon tool, I must press and hold the shift button down. See, I'm now capturing. See, using the area tool, you cannot capture something like this because it's always a rectangle. It's easy to use, but it's always a rectangle. So the polygon tool enables you to capture something that you cannot easily capture with the area tool. Okay, that's the purpose of the polygon tool. And this is the text I can put. You can work out very easily what text means, but I'll just show it. So you can change the size. You can also change the color. Right click and change. So you can highlight the important parts of your drawing by using the colors and font size and so on. So having done this, what I can do, right click, delete area. So that's completely gone now. I can move the text and so on. All these things are very, intuitive, and you can pick them up very, very quickly. One of the things I said was, let me do the calculation just to make sure that I haven't actually messed up anything. Okay. Was this elastomeric valve is a very versatile tool. So if I actually have a look at the 3 control valves, or the elastomeric valve, sorry. So you've got PIPENET actually calculates, this is brilliant because it calculates the CV at the operating point of the control valve. It gives you the inlet pressure, the outlet pressure, the delta P, the flow rate, and the CV. So if you actually want to replace or if you're going to use orifice plates, you can estimate how the orifice plates should work, or how you would choose the orifice plates by using this. So I'll show you how you would do that. I've written that down, by the way, these 3 values, the delta P, flow rate, and the CV at the operating point, because the CV of the valve is going to change depending on its position. And these are the CVs at the operating value of the control valve, basically. So see, what I'm going to do now is the opposite of exploding a node. I can also reconnect nodes, but I must make sure that I merge the nodes, okay? And then I pick up the orifice plate, and place them here. See, I know for my table is from the previous calculation. Oops. This orifice plate, that's the pressure drop. I can actually either define the pressure drop or the diameter. So you can actually work with the diameter specified, in which case PIPENET will calculate the delta P. See, I've got the orifice place here, but there's no flow control. There's no flow control valve. So let's see, you know, would be very interested to see with these orifice plates what actually does happen. See, it's giving the exact flow rates I require. This is a good way to size the orifice plates in order to do flow balancing. In other words, use the elastomeric valve first and determine the delta P that you need in the orifice plates to balance the flow, and then estimate the size of the orifice plates. So if I click on that orifice plate, see, it gives you the diameter. In order to have more decimal places, I have to do this. See, then you have a more accurate value for the diameter. So in the orifice plate, you've got the pressure, drop the orifice diameter and the pressure at the throat of the orifice plate, because of the minimum pressure, because you need this in order to assess if there is likely to be cavitation in the orifice. This seems to be quite safe because the makeup tank is imposing quite a high pressure on the system. So this is how you would actually design orifice plates in order to balance the system. Okay. You may also have, if you remember, I mentioned that you may have throttle valves. How do I do that? Okay. Now I'm going to use a control valve. Why am I using the control valve? I mean, I can actually model how the control valve performs, or I can even use this to model a throttle valve which is manually adjusted, okay, which is a lot cheaper than a control valve. So I'm going to click on that, and I'm going to specify the attributes. See, from the previous calculation, I know that the CV at the operating point of that valve is 131. I've written all that down, and of course I'm going to choose a valve that's bigger than that, because if I choose exactly that value, the valve is going to be fully open when the flow is what is required. We don't want that. We need a valve here which is only partially open when the flow rate is what is required. So what I will do is to input a CV that's slightly bigger than that. We need 131, so I'm going to input 150. And the required flow rate is 350. I can display the pipe 4. So what is, now I'm specifying, I've got a CV which has a CV, sorry, a control valve which has a CV of 150 when the valve is fully open, but I want the valve to control the pressure, the flow rate at 350 in pipe 4. Here, the CV required is 168.4. That's the required value when the valve at the operating point. So that must not be the CV when the valve is fully open. So when the valve is fully open, this is quite a big value in comparison to what is required. The flow rate is set at 300. As on pipe 5. That the ideal CV, or the CV when the valve is at the operating point, is 242. 0.5. So I'm going to choose a valve which is a bigger CV than that. Flow rate, because the flow control valve, and that's 250. That's on pipe 3. That should be sufficient. Because the flow rate is exactly what I want, and I can look where the pump is operating and so on. So what I can, if I click on that, what do I get? See, I get the flow rate, which is what I set here. So the valve setting is normalized, so it's between 0 and 1. 1 means it's fully open, 0 means it's fully closed. So it's about 87.5% open. And remember that this valve was very big. So it's only 58% open. And that is 86.6% open. Now, you see, in reality, these things do not have to be control valves. They could be manually throttled valves. But what this tells you that if I choose a valve with a CV of 280 when it's fully open, then I must throttle it to 86.6% open in order to achieve the flow balance. So simply because I put a control valve here doesn't mean that it's a physical control valve. It could be a throttle valve, and that tells me the position of the throttle valve in order to achieve the flow balance. Okay? And as Victoria said, if you have any questions, please ask them through chat or indeed send an email. Okay, now let's go to the next example. It's a base case. That's the system I want to consider. And these are the cases I'm going to consider. They're all to show different features of PIPENET. You know, the system is working normally. One pump fails, and if it fails totally, and the other pump does not respond, then the system cannot work. The second pump responds on pump failure, but it works at full speed. The second pump actually starts up, but it's a variable speed pump, and the speed of the pump is controlled. It's called heat exchangers, conversion to transient, and I will run the transient module just to show you how it is. The aim of this is to show you how we can import a model from the standard module to the transient module and then perform calculations, dynamic calculations, because it's something that we would very often do, because you know, we call them design and analysis. Design is for estimating things like pipe sizing, pump size, and so on. You can do some simple cases like pump failure and so on, but in steady state. Okay, going from steady state to steady state, and whereas inevitably you would then go on to analyze how the system you've designed behaves, and that we call analysis. And the transient module is very much aimed at analysis, and they are two sides of the same coin. So you would generally set up the model in the standard module, fine-tune your design because it's very fast and it's very simple to use, and then you would go to the transient module to do a dynamic analysis in order to check how the system will behave under pump failure, valve closure, pump startup, and things like that. So they're both two sides of the same coin. So let's go to this. So that system, you know, it's here. Basically, there are control valves. You can see that there are control valves, but what I could also do, if on that pipe, for example, if I had a valve which is not going to be operating, if we had a gate valve which is fully open, I can simply add that as a fitting. This is the fittings data from the crane manual. We also have our own fittings data. So that's how you would do that, but these valves are not strictly necessary. I've got them here because when I move this to the transient module, I might wish to operate these valves. Okay, and that's why I've got control valves here. On the other hand, these control valves actually, see, look at the difference. I click on that control valve, it's fully open, fixed. There's no pressure control. I'm just assuming that's fixed. All the valves are like that, except for these 4 valves. And these 4 valves have the flow set point and the pipe label. If I display pipe label, the pipe 42 is here. So this valve here is controlling the flow rate in that pipe to 3,000. 5,000 in 98, 3,000, 5,000. So the total is 16,000 cubic meters per hour. These are actually quite big pumps. So they are actually variable speed pumps. And you can see that the pump setting is not 1. What we're saying here is that it's operating at 74.2% of the design speed. See, the output actually has 2 graphs. That is if the pump is working at 100% RPM. That's what you're getting. But if it's working at 74.2% of its full speed, then that's the pump curve, and that's where you're operating on that pump curve. Okay, so this is how you model variable speed pumps. you can change the pump setting. You can also have a variable speed pump with control. I will show that later on. What we note here, I can click on that. I can see that the pressure is 4 bar. Keep that in mind because we will use that later on. So what I'm going to do now, as I said, see, I can switch off the pump. No, that's the best way to stop the pump operating. You can see that PIPENET has put a dot in the pump, and that says, that tells PIPENET that this pump is not operating. It says failed. See, what this means is that it is not a feasible system, because this pump working at 74.2% doesn't have the capacity to flow 16,000 cubic meters per hour. That's what that's telling me. You can check that. Yeah. You know, if I change that to bar, see at 4, it's just under. That's 16,000, which is required. So that is, sorry, this is at working at full speed. But if it's working at 74% full speed, the flow rate will be much less than this. And that's what is saying that it is not able to generate that required flow rate. That's why it failed. So what I'm going to do now is to say the pump is operating at full speed. It's fine. See, that's a pump curve. There's only one curve because it's running at full speed. And that's where you're operating. Okay, and what we note here is the power consumption. We'll have a look at this power consumption later on in another example, but it's just something that you note. But you see, in this case, we have a variable speed pump, so we may not want to go to the full speed. So what we can do is to say, we have a pressure sensor, and that's going to set the pressure at 4 on node 2. See, now it's running. See, why am I showing this? It's because what's telling me is that the control system for the variable speed pump must be designed in such a way that if this pump fails, in order to maintain the required pressure there, which is 4 bar, this pump must be set to operate at 94.5% of its speed. And you'll see that the power consumption has reduced a little bit. That's the main purpose of a variable speed pump, that you have more flexibility and also the power consumption is less. So 1644, remember that. See, 2000. So it's quite a lot of power saving, because the speed actually doesn't change that much, but the power saving is quite considerable. Okay, so in this way, you can optimize the way the pump operates. Now, you can also, of course, use this to select the control valve. This valve setting, for example, is 56%. With both pumps working, it was actually probably different. So this control valve here is 50%. If that fails, let's just consider one case. I should have set it to 74%. It doesn't matter. Let's run this. CUC gives you the position at 26.7%. So in this way, this helps you to design the control system for this in preliminary design at least. And because you can see how the control system, the flow controller for this will work. Okay, so there are a lot of things you can do in the standard module, even when it comes to dynamic type applications, like the choice of the controller for the variable speed pump and the flow control valve here. But of course, you must then go on to the transient module to do a proper analysis. How will the control valve respond, and so on. So I've also got a case where I've got heat exchangers. This is simply out of interest. I've designed the control system without heat exchangers, and then I decided to insert the heat exchangers. You can see that I put them in here. It shows you how the temperature changes. 15, after the heat exchangers, 26.5, and it remains. When it comes to heat transfer, there are two kinds of heat transfer. Atmospheric heat transfer means heat transfer through the walls of the pipe. So that'll help you to, select the lagging or insulation, as it's called. Or heat transfer means a point heat transfer, such as a heat exchanger, adding or removing heat from the system. And that's what we've got here. There are 4 heat exchangers, we can see. So that's the complete system, including the heat exchangers. Okay. And what I'd like to do next is to move this to the transient module. For that, we have a conversion tool, utilities, convert to transient. By the way, you can also export the results to Excel or even a comma delimited file, because then you can do further analysis yourselves if you wanted to. There is also a scenario manager, and we haven't got time to look at that, but that's more for this is more useful in the transient module, because in the standard module the calculation is so quick that there's really no point in defining several scenarios for PIPENET to automatically run. It's much better for you to run a case, look at the results. You don't like something, change it, rerun it. And that's the best way for the standard module. When it comes to the transient module, if your network is really complicated, then it may take a few minutes to run, in which case it makes sense for you to create a number of scenarios, run them, and look at the results later on. But as I say, I won't do that today because today is mainly about the standard module. But I will show you this. It is not necessarily going to convert what is here. I can choose the data file that I want to convert. So I'm going to choose this one just to show what happens. See here, that's the name of the data file. This is the name of the data file, but it's put TM, the transient module, at the end of it. We'll convert that. Conversion completed. Close. This is the file that I just created, by the way. You can see it's 8:42 in the morning here. So that is, now we're in the transient module. See, these valves, I introduced them as control valves in the standard module because in the transient module, I might wish to see what happens if this valve closes or opens and things like that. So anything that's going to operate in the transient module, you will use the operating valve model, and that's here. It's called operating valve. The pump, by default, is a variable speed pump, and that is the node through which I will specify how the pump is going to operate. Okay, in the standard module, we didn't have these nodes because we didn't have to tell the dynamic aspects of how these things are going to work. Okay, and these are control valves. In the standard module, we did not have control loops. We just said, or dynamic control loops, we simply said the control loop will be such that this valve should maintain a flow rate. That's all we said. But for dynamic analysis, you need to know the characteristics of the control loop, such as the PID controller and so on. So I input them here. See, these are true control valves, so they've got control loops, where these are simply operating valves, And in this scenario, they remain fully open all the time. And let's look at this control loop. I'll do this very quickly because it's not the main objective of today, but this is something that you should be aware of. That's a pressure sensor that picks up the pressure of that node as a transfer function, which actually models the dynamics of the pressure transmitter. Because if the pressure at the inlet of the transmitter changes, the output signal from the pressure transmitter does not change immediately. It takes time to respond. And the transfer function models that. The PID controller is here. And I'll come back to that in just one moment. And there's another transfer function here, which represents the dynamics of the pump. Because the PID controller tells the pump change speed, the pump doesn't say yes sir and change the speed instantly. It has its own dynamics and it'll take time to respond, and that's why we have the transfer function. We look at this more detail. We have one webinar planned for control systems, and we will look at these in more detail during that webinar. But if I click on that, just to show, see that's a PID controller. You can have any combination P, I, D, and so on. But this is a controller with all three terms, and these are the parameters for the controller. So you can have things like the tracking time, and that's for the integral term, and you can have anti-wind up, rate time, and so on. So you have all these things that are essential to define a PID controller. Now here you see, what am I going to do here? In this case, what I want to look at is to see if there is a total power failure, how does the system respond? In other words, the pumps lose power and they're variable speed pumps. So how is it going to respond? And you see, this is a very important scenario in cooling water systems. Why? Because especially large cooling water systems, see, there are cooling water systems which are modeled in the transient module, which have got 4.5 meter diameter. It's a tunnel rather than a pipe. 4.5 meter diameter. It's huge. And such huge pipes are normally made of fiberglass when it's a cooling water system. So pump failure, see, when this pumps lose power, they will actually act as resistors in the system because the fluid is trying to keep the pump rotating, and it's like dragging somebody, you know, and the pump says, oh, I want to stop, I've lost power. But the fluid says, no, you're not going to stop, I'm going to keep you moving. So you see, as a result of that, you get vacuum pressure in the pipes, and that vacuum pressure can make the pipes collapse when you have such large pipes and there is pump failure. So this pump failure is a very important scenario in cooling water systems, particularly the large cooling water systems and the pumps lose power. So I click on that. See, the trip time is unset. So essentially, this is a steady state case because see the pressure here, it's set. To constant value. The pressure there is set to a constant value. So it's a steady state. It's worth it running the steady state case just to make sure that I've set up the system correctly. What do I want to do? I want to check the speed of that pump. Pump 1. That's the actual rotation speed. That's the pump proportional speed. See, this is what we had in the standard module. So this should be approximately 0.742. Do you remember that when we did the steady state calculation, we set the speed of the pump at 0.742. I'm just double checking that that is exactly what I'm getting. And then I will just run one scenario. See, this, the most dangerous case with fiberglass pipes is a total failure, total power failure. And that's what I'm looking at here. See, the inlet pressure is fixed at, it's the same, except the pump trips at 2 seconds. I'll be particularly interested to know how this pump spins down and the pressure, you know, in this part of the system. Okay, so I'm going to run that. See the outlet pressure, you can see pump loses power, zooms straight down. It'll ultimately settle down, not at 0, at 0.3, because the inlet pressure of the pump is 0.3. It's getting close to that, but it'll go up and down and ultimately settle down at 0.3. That's what we're looking at. Let's look at the rotational speed of the pump. The rotational speed of the pump might not actually be 0, but in a case like this, I would ultimately expect that to settle down at 0. Why am I saying that it may not be 0? Because the inlet pressure is 0.3. So it may keep the pump running at a low speed. So the pump may simply be ticking over. What's interesting is to look at the proportional speed. You see this, the difference is, this is the signal that is coming out of the control system. See, that's a control system that has an input to the speed of the pump. What it's going to say is this. You see, it's looking at the pressure. So when the pump loses power, the pressure is going to go down here. When the pressure goes down, the control system says, hey, the pressure is going down. We can't have that. So the pump must speed up. That's what it's doing here. The pump speeds up, or the control system tells the pump to speed up because the pressure is going down. The poor pump responds by saying, hey, I'm so sorry, I've got no power. You can ask me to speed up, but I cannot do that. I've got to spin down and either stop or just be ticking over. It depends on the pressures. Okay, so that is what we're doing. This is a fantastic, you can put labels. There are lots of really lovely things here. You can go and in some cases there'll be rapid oscillations, in which case this will be very, very good to have a look at this magnifying glass and so on. Okay, so that's how I would model the transient case. I'm not going to go through all the cases, but you will get the data files. By the way, one of the things that I would add, as Victoria said, that for the attendees who are our customers, we'd be very happy to send you the data files, because with the data files, you can open these examples because you've already got PIPENET. You can open these examples and run them. Okay, so do ask for the data files. Also, as Victoria mentioned, she's recording this session, so you could ask her for the recording as well. Victoria will explain all this at the end. I'm just mentioning that as we go along. So this is the, the open loop cooling water system. I've explained many things here, a lot of things. So let's go on because time is pressing on. So let's go on to multiple LNG. Train. This is a massive system, huge. Look at this. It's 3 meters. Sorry, it's more than 3 meters. 3.5 meters diameter. It's not the biggest, because biggest I've seen is 4.5. But what this is modeling is a number of LNG trains, cooling water system for a number of LNG trains. They model the LNG trains as these, like these control valves. That is the flow rate that they've allowed for each of the LNG trains. I think they're all the same. Maybe these are different, I don't know. Yeah, it's slightly higher flow rate. So they modeled the LNG trains as control valves. They have not modeled the pipe that's, at the boundary of the, or inside the boundary limits, that the network within the LNG, the train, they've not modeled. Okay, they've simply did a macro. They've treated it like a black box, if you like. See, the inlet, they expect the pump to generate a pressure of 3.7. But at the outlet, see, this is during one of the stages in the design. It's not the final design. They want to select the pipe sizes and so on, and the pumps here, which will generate a pressure of 1 bar gauge here at the outlet. So the inlet pressure is 3.7, and you've got all these control valves which will fix the flow rates, and you want a pressure of 1 bar gauge at the outlets. And this is they've already selected the pipe sizes. This is the precursor to selecting the pumps, because once you get the flow rates here, you've got the pumps, because you've got the pressure here set to 3.7. Okay. You can see the size of the pump. 64,000 cubic meters per hour. That's huge, isn't it? And there are 6 of them. Sorry, 7 of them. So 420,000 cubic meters per hour. So, can you imagine that the system in 2.5 hours is going to pump 1 million tons of water. 1 million tons of water in 2.5 hours. That is how big the system is. See, it goes without saying that you would use a variable speed pump here because it's going to consume an enormous amount of power. Okay, but let's make a quantitative assessment of that. The next case I've got is the same system. I've added the pumps because from the previous case, I know the pressure and the flow rate. See, I've added the pump curves here. I think we needed about 66 at 3.7 bar or something like that. So it's slightly bigger than the minimum which is required. I just want to make sure the inlet pressure, of course, is set to a small value because previously it was 3.7, don't forget, because that's without the pump. So the pumps have a slightly positive inlet pressure. So if you look at the pumps here, is operating close. That's simply because I specified a very narrow range. And the pump's operating more or less at the minimum flow rate value. What I'm really interested in, 2 things. One is it's a fixed speed pump, so it's running at 100% RPM. The power is 7,560 kilowatts. You would expect that because they're huge pumps. The scope for reducing the power consumption by using variable speed pumps. So in order to make a cost justification, you want to see what will happen if I had a variable speed pump. You can do this in the standard module. Do you remember that the design case was to have a pressure of 3.7 bar gauge at this node. So I've taken the pump and I've said that the pressure control and the speed of the pump will be such that it's 3.7 bar gauge at this node. See that you can't see that very clearly. So let me increase the font size. See, that is, you still can't see it very well. IG1/1, okay? So that's what I've done. I've said that the pressure or the pump speed will change in such a way that IG1/1, the pressure will be 3.7. And I'd be interested to know what speed the pump should operate in and the power consumption. The speed, because that'll help me to design the control system and the power consumption, so that then I can do a cost justification for the variable speed pumps. So this shows a lot of things you can do. I mean, you can even do a basic design of your control system using the standard module. See, 6393, and the pump is operating at 95.2% of full speed. So you keep this in mind, this 6393. That's what we're getting. In the previous case, see, 7560. So it's quite a big saving in the power consumption, even though the speed is only changing slightly because of the flow rate so high. And cooling water pumps are normally have a low delta P, and that's why you can use fiberglass pipes, because the discharge pressure is not very high. So the flow rate, if you trim the flow rate, you can change a huge amount of power, and that you can see here. So in this way, you can make a cost justification for the variable speed pumps without actually doing the dynamic analysis. Okay, so I'll quickly go through some applications. It will take me another 10 minutes or so. I apologize for taking a little bit more than the scheduled time, but I'm sure that it's useful to you. So let's have a look at the next example, which is a steam system. See, these three systems you're looking at are cooling water systems. This is a steam system. And what it is that we need to have a certain pressure, because it's a battery limit, and we want to be able to provide a certain minimum pressure there, 6.37 at that flow rate. And we want to find out what flow rate and pressure are required here. See, that gives me the flow rate and the pressure. It's quite a big system, 56.9 tons per hour. And it's 7.34 kilograms per centimeter squared absolute. One thing I'd be interested in is to see what happens if for some reason that pipe is blocked. It could be that a technician closes a valve to do maintenance, and he forgets to open the valve. Or it could be a physical blockage. You see, there's this block. That's why I'm doing this example, because we've not done a case where we blocked a pipe. You must be careful when you use things like block, because it could potentially create a case where the system is is infeasible to solve the problem. But anyway, we block the pipe, and we've looked to see we need a huge pressure, because it was around 7.3 if that pipe is blocked. So you see, you can have, and of course, we have to generate the same pressure and flow rate as before. So it says that if this pipe is blocked for some reason, it's an important pipe, because in the middle of the system. How does that affect the supply pressure and flow rate. That's what I'm looking at here. Next one. Chill water system on a ship. So that's inlet, 12 degrees centigrade. In this case, there are two things. I want to make sure that the heat exchangers can get the required flow rate. And secondly, I want to size the chiller unit, which is here. The chiller unit depends on the flow rate and the delta P. So the return temperature is key. Okay. It will calculate the return temperature. It will not use the return temperature here because obviously, because the heat exchangers, the temperature will change. Pressure is 12. Sorry, the temperature is 12. Pressure and flow rate are given. Of course, the flow rate will be the same, but you can see that there is a pressure drop and there's a temperature, here. And so you can see the behavior of the system. In particular, I'm looking at the temperature there in comparison to the temperature here. Okay. So what I want to see is what happens if I block or take some of those heat exchangers offline. I'm just choosing some heat exchangers at random. So, and I want to see how that affects the return temperature. Is 13.8. So I can, see how the chiller unit must be designed, because if one case all the heat exchangers are working, in another case some of them are not working, then the chiller unit should be able to cope with that, a number of cases like that. And that's the aim of this simulation here. And of course, the more basic thing I've looked at is the flow rates, just to make sure that all the heat exchangers are getting the required flow rate. That is, of course, the more fundamental aspect of the calculation. See what a system is. Something we've already, these are all real systems, but here we are only considering the, the lower decks of the system. We're not considering the complete. The system, including the users and so on, is a basic, it's the same level as a sea chest. As you can see that there are 4 sea chests here. The basic aim is the sizes of the pipes. That's really not affected very much by the elevation change. So if you look at the elevation here, see all the elevations are 0. You remove that. Okay, so they're not considering the elevation because the aim is pipe sizing here. It's a very small system. So you've got small diameters here. See this 20, 15, and so on, a non-preferred size. 65 is also a non-preferred size. So as we did before, even 25, I may want to avoid using. 32 is definitely a non-preferred size. And 65, non-preferred size. So I've got all the pipe sizes now designed as I want. Let's say seawater system. Methane, I won't run this. I'll just explain what it is. See, this is a methane gathering system in mines. That mines collect methane and it's extracting the methane. That's a pipework for that. And the main purpose of this is actually to size the fans for collecting, extracting the methane. What's interesting in this is that the operating company in this case, in order to save money, they wanted to use the same pipes in the water pumping mode, because if the water collects in the mines, you don't need another piping system to pump the water out. You can stop gathering methane and run the same piping system to pump out the water from the mines. So that are the two cases they considered: methane extraction and then water collection. These are the two things that they considered. The last example I want to show is this one here. This is a relatively complex system. It's not the most complex, because see that it's got 867. What makes the system complex is that it's modeling a large number of control loops. See, each heat exchanger has a control loop except one. And control loops, as you can imagine, are difficult to solve. And so it'll take time. So that's the last example. I will run it. And while it's running, we can have a look at some of the features of the system. See, then I can look at the system like this. You can see how complex the system is. Anyway, it's done the calculation now. So I can look at the results and do whatever I want to do. Anyway, I've said everything I want to say, and once again, I'd like to say it's wonderful to see you all. We love our customers. We like to keep in close communication with our customers, and so it's wonderful to see you all. And you can see from my voice that I do mean it. We love our customers. We want to be close to our customers. So I'll hand you back to Victoria now. As we said earlier, if you have any questions, I'm sure that you've asked them through chat, but if you have any questions which require a detailed answer, we may respond to you by email, or you're most welcome to send an email to us, and most of you will know the email address for support. Oops, just said .com, where you already know that. So it's supports@sunrisesys.com. Okay, that's the way you contact us if you want to ask any more questions in more detail. Victoria, I'm happy to hand over things to you. You're still here?
Yes, Dr. Sebastian, thank you very much for delivering this excellent session. And I'm sure our attendees today learned new things and interesting things, and they received answers to their questions. And I would also like to thank to my colleagues, Dr. Legend and Chelvi and Shaliha and Wissam, for being here with us and answering the questions. So if the attendees have any more questions, please contact us by email. So write either to support if you're a customer, or just write to pipenet@sunrisesys.com if you have any inquiries, including any commercial questions. So today's session is over. As we promised, we would share the video recording of this session later, most probably next week. So please look out for an email from me with a link to the video recording next week. We will also share the materials next week for today's session. And if you are an existing customer, we will share the files, the actual files, so that you could open them and play around with the same examples as you saw on screen today. We can provide training certificates, the certificates of attendance for today's session. So if you would like to receive it, please send me an email. Please send that email to me, to my email address, which is victoria@sunrise-sys.com. And I'll be happy to send you a certificate of attendance as soon as possible. So as I mentioned before, we are planning many other webinars this year, and they will be webinars on spray sprinkler module and transient module. So if you or your colleagues would like to join those webinars, you are most welcome. Please look out for invitations from us. Please share those invitations with your colleagues and invite all the relevant people to whom that might be interesting. Okay, and today's session is over. Thank you once again for giving us your time, for participating. And we look forward to hearing from you and seeing you at our future events. Today's session is over. Have a nice day, have a nice evening, and we look forward to hearing from you and seeing you at our future events. Bye-bye.